So I don't feel like we need to spend too much time on the logistics because, well, everyone has taken 17A and or B at UC Davis, right? Okay. Everyone on Zoom, right? Raise your hand if you haven't taken 17B and 17A at UC Davis, or I guess 17B is the one that matters most, right? Everyone's like familiar with UC Davis. We don't have to go through all like the welcome to UC Davis. And yeah, we're good. We've got this down. We're students here. We know what's going on. So we'll briefly, very briefly just talk about the Canvas stuff. And then we'll move on to just talking about the math. So the nice thing about this particular section of our class is that there's only one class, right? There's only one 17C class. We're not like all spread out across 5 different classes. So all the information, I mean, we're not going to get off track from another. It's just one class, which is awesome. It makes life easier in some ways. As far as the co-class, here's the main page. Here's all the usual information about where to find me. I'm available in many ways, shapes, and forms. I have office hours, Mondays and Wednesdays, 11 to noon in C class, Mondays and Wednesdays, every day from 3 to 4, Mondays and Wednesdays in math drop-in, which is in the library, Tuesdays, Thursdays, and Fridays in CADS, which is the Center for African Diaspora Student Success, which is over on the second floor of the South Silo, and C classes on the second floor of the MU. Yeah, all that stuff is stuff you could read later on. This is stuff more for like the other classes I'm teaching, but you know, everyone kind of gets the same syllabus. So I'll post, come on in, Co-17C. I will record classes I'm doing right now and post it on Canvas later on. So if you missed something or couldn't come to class at all, you're welcome to watch class there later. You're also welcome, as people are. Oh, my screen sharing is paused. Sorry, 1 second. Let me resume sharing. That's weird. Just share screen too there. Cool, that'll work. So I was saying, you're welcome to attend class in whatever it looks for you. Obviously, I think in person is great because I like seeing people in person. Come on in. But if you aren't feeling well, want to attend via Zoom, that's great. Right? If you're feeling well, you probably shouldn't attend in person. So attend via Zoom if you're not feeling well. Or if you don't feel like coming to class, I get it. You can attend live via Zoom, or you can attend later on. You can attend, right? You can watch the video later on. That'll count for your attendance. Why do we care about attendance? Because if you're enrolled in, I should say, if you're registered on Schedule Builder for this class, the way you pass this class is by attending at least 75% of the classes. So that's why the only reason, well, it's one of 2 reasons we care about attendance, is that if you're registered for the class, you want to pass it. I want you to pass it. So please do fill out the attendance form when you attend the class. Oops, where'd it go? Actually, let me just go to it for a second. Right there. So on the attendance form, you'll write your email, your ID number, your name. I would write James Parmenter, my first name first, my last name last, the class you're attending for, how you attended, and then, and that's what we don't, come on, don't be that way. And then the bottom, the date of the class you're attending for. So if you didn't actually attend right now today, let's say you watch this video tomorrow, you would still write today's date. And so if you watch this video on Friday because you weren't here today, maybe someone out there is watching this tomorrow in the future, you would still write down the date the class actually occurred on. It makes it easier for me to figure out what's what. So that is why you should fill out the attendance form. The other reason you should fill out the attendance form is because the academic assistance and tutoring centers get some of their funding because of how many students we serve. The more students we serve, the more we're able to say to our, overlords that we are serving students, give us money. So that's another reason we can keep track of what people we serve, and I then report that information to my supervisor. So please do it for that reason as well. All right, back to the, and we're going to get to the math. Don't worry, the math is going to happen. Just doing this first. What else? Video recordings. You've taken math classes before. Where can you get more help? So there's me, office hours, there's Grant's website, which if you've taken the 17 series, you've probably been to Grant's website before, but if you haven't, you should check it out. It's got lots of useful information on it. You go to our AATC website for information about math stuff. You can make an individual appointment with me. You can't right now because my schedule isn't available at all. But if you want to make an individual appointment, you can with me to either meet in person or via Zoom. And then where else should we look here? We should look at the modules. So that'll show up later at the end of the class. Useful links, top link to the attendance form, fill it out every time you come to class. And then there's the links to the class notes. I'll also probably post them in Canvas, but they'll be on my Google Drive as well. Grant's website again. My YouTube playlist will have these class recordings and old class recordings. So if you think I might have done it better last time I taught, you can go watch that. I probably did it just as well last time as I would do this time. Other video lessons we recorded a while ago for 17C, which are still probably useful. Oh, some graphing links, these are good. So here's a link to, so it's kind of like, it's not like Desmos's 3D graphing. It is like kind of a little application someone made up in Desmos for 3D graphing, which is useful. I think it's kind of neat. 3D graphs in GeoGebra is probably better though. These are just like the more official one. And then later on in the quarter, when we start graphing the direction field or phase plane for a system of linear differential equations, we don't do a whole lot of graphing of it, but we do some. It's nice to actually be able to see what it really looks like. So you can go to there and graph that as well. It's kind of, I mean, it's not like the best ever, but if it loads, it's pretty good. So you can do, like, for example, here's some linear differential equations. You can graph it's like, oh yeah, and then it kind of shows you like the spiraliness of it. It's fun. Later on, we're going to be looking at some systems of differential equation and trying to determine whether or not the system is a spiral or a node or other things. Those are really the only things. But like, is it an inward spiral or an outward spiral, or is it an inward node or an outward node? And it'll be nice to kind of see what that actually looks like, in addition to just using 2x2 matrices to determine whether or not we have what kind of matrix, what kind of system we have. So there are going to be, we're going to come back to the 2x2 matrices and the eigenvalues and the eigenvectors and all that kind of good stuff, or not so good stuff. So let's close that. That's later on. The modules. What else is in the modules? And useful links for graphing. Some exam prep material, which isn't available to you yet, but will be. Oh yeah, and then later on, the last week of the quarter, we will probably do some probability stuff. Sometimes I don't think I've seen anyone cut it out yet. So you'll probably at the last week have to do some probability stuff. This is a nice terminology for probability page. It's got like, there's a lot of probability examples that have to do with like poker, because it's just it's a realm where it's easy to make up probability examples. But to be able to kind of answer the questions, you have to know what things mean in the game of poker. So this has some of that. It has some biology stuff too, because there's lots of biology probability examples, which are probably more germane to this particular class, right? It makes more sense to use a biology example for biology for calculus than it does to use a poker example, but people's habits die hard. So it's like, yeah, poker, easy examples, or easy to think of examples at least. Oh yeah, and then there's this 3 girls problem that your teacher may or may not give you, but it is it's always a challenging one. So I have that up there still, but that'll be later on. I think there are no assignments other than attending class. So when you fill out the attendance form, I will try to fairly regularly, at least once a week, probably more often, update your attendance in Canvas, because it doesn't happen automatically. Like your attendance form you fill out will then populate a Google Sheet, which I will then go look at and fill in your attendance on Canvas so that you can see your attendance having been marked. If something is ever off with your attendance, just let me know. I'll fix it. Questions, comments, concerns?
So if we're not like registered for the class, we don't have to do the whole roll call.
I still need you to do the roll call attendance because of the second reason for attendance, which is that we use the numbers of students that we serve to help make a case for the fact that we should be better funded.
So we should use the one that's on there.
They're the same one. They're the same. They both get you to this attendance form here, which should look like this on top. I picked a different picture on top to differentiate. Like if you click on, in fact, let's find out. I'm curious. What does this look like? I feel like in the top doesn't look like it looks like that. And they have a different, so that one looks more like UC Davis official. So if you look at that one, there it'll look like, this on top, looking very like UC Davis academic distance tutoring official. That's not the right one. The one from our class is specifically. So if you see that, you see my name right there, you'll know you've gotten to the right one. Again, if you do the wrong one, we'll get it worked out. It's not a huge deal, but I at some point have to report back numbers of attendance, or actually really have to like insert your student ID numbers into this form and then click a couple buttons and do that a few times. But it's not that hard for me. It's not that hard for you either. What else? What else?
Sorry.
No.
Are you following like a specific professor?
There's only one.
Oh.
Which just makes it easy, right? So yes, you were all in the same 17C class, I believe, right? There's only one. I believe it's with Rishi. Last name Chaudhary, I think. Yeah, the pronunciation I apologize for. But yeah, I think he's the only one. Let's double check just to be sure. Math. It's good to know what you're in for. Courses. And I think he's not actually in the math department, which is totally fine. Oh, okay. I wasn't sure. I know because I looked him up to see. But yeah, I think he's the only one teaching 17C, right? We've got, yes, section 801, 802. Yep, it is him all the way. So that's who you've got, which is nice in that we will all be at the same pace, right? No one class is going off into the flight speed ahead or way behind. We're all together. Yeah. What else?
So I came in late.
Sure.
So I wasn't sure. So just to clarify about the attendance, we just fill out the form that you showed us for the grades, right?
Right, and it should look like this, and you can either access it on Canvas. Most easily, in my opinion, it's the first link you should be able to see in the modules, or by scanning this QR code. Anybody on Canvas? Anybody on Zoom have any questions? You guys are always welcome to type a question in the chat, or if I don't see it, I'm ignoring you. Something needs to be addressed. You can unmute yourself and say words. That is totally fine. It might scare me, but that's okay. Yeah, as long as I have the volume turned on. Yes or no? Okay. You guys had classes today, right?
Mm-hmm.
I imagine you mostly talked about just kind of class logistics.
There was no math.
No math. Okay, that's pretty typical. So let's see. What's that?
Oh yeah, I was just surprised that like there was no math because Thomas, like last quarter, he
Sure.
was just writing like and Lee.
Yeah, I mean, people are different. I think this might be the first time he is teaching this class, so that could also be part of it. All right, so you're always welcome to ask questions about class logistics, about math, a few things. I will try not to make mistakes, but occasionally when I do, I'll probably make the most mistakes. If you see something that looks questionable, let me know. I will either tell you why it's right or tell you, oh, I'm wrong, I made a mistake. It's not a big deal. What else? If you can't see something that's on the board, because like I'm writing down here where you can't see, just let me know. It'll happen probably multiple times per class, and I will try to be good about it. But sometimes I get too focused on what I'm writing, and it's hard to see up over there. So yeah, oh, that's right. That's why I was doing something in my previous class where I had the screens mirrored, which I do not like as well. But the one plus side was I can see what I'm writing over there. But it's less than excellent, so we will not be doing that. Let's see. Let's go ahead and see if we want all these slides. Let's let's do a few things first here. Let me make sure I'm sharing the right thing. Oh yeah, I'm sharing the whole screen. Great. Let's go ahead and minimize this. Maximize this. Let's see. I feel like in the past, we need to turn off this front light. It's maybe a little better to see. Actually, let's. I'll need your opinion. Is that better?
Yeah.
Or is that better?
Darker.
Okay. It does feel more conducive to taking a nap,
Yeah.
which is probably not ideal, but we'll work with it. If it's too nappy, we can always turn the lights back on. So where did I want to start here? Let's start with something that's kind of just a reminder of some stuff you did in 17B. So how many of you took 17B last spring? Okay, so I think that is actually literally everyone. How about people on Zoom? How many of you on Zoom took it last spring? Okay, so I see I'm getting one thumbs up. All right, yeah, all three. Great, everyone took it last spring. So we're all very much on the same page. I imagine you might have all had the same professor last spring because there was probably only one or two people. Oh, okay, there were two. Okay, so we're all very much in the same place. We've had a whole summer of not doing any math. So let's remind ourselves of a couple things we purportedly saw in 17B. What is this? What? That's weird. I don't like that. Why are you in view? Let me see one more thing here. Can I do that? That just feels. Usually this little base part is not so visible. Oh, maybe it's because I'm usually vertical. I don't really want to be vertical. Do I want to be vertical? Decisions. No, that's terrible. Don't do that. Okay, sorry, just trying to work things out here. Let's try it that way. Okay, great. Good times. As you can see, right, I have orientation problems sometimes. All right. Oh, also, I know what I want to do, and you all can still see me face. You'll see a lot of the back of my head, to be honest, but yes, okay. Great. Had some examples. My notes. Cool. And I can see his homework assignments as well, which is great. So I think we should first start somewhere that might be somewhat familiar, which is finding some eigenvalues. This table's a little high. Finding eigenvalues of 2 by 2 matrices. Fortunately, in this class, we only ever have to deal with 2 by 2 matrices. We're not going to typically deal with larger matrices. On this first homework assignment, I did notice that there are a couple problems where you have to, I think, add some 2 by 2 matrices together, or subtract that, or sorry, bigger matrices, 3 by 3 matrices. It's not that big a deal. It should be fine. We can look at an example of that too. So, but let's talk about what's actually important, which is finding eigenvalues of 2 by 2 matrices, because that's something you are going to be doing later on.
Do you have access, that's like the homework that we have?
Yeah, this is totally the homework that you guys have. It might have different numbers. Sometimes people do the thing where it's numbers. No, this is totally homework assignment number 1 to September 30th, 2022 at 7 p.m.
Oh, cool. How many questions are there?
There are, so I will say that there are 15 questions, but some of them have a few parts. Like question 2 says, choose the correct geometric description of the set of points in R3 satisfying each expression, and then there's like 8 different expressions. Or question 3, there's like 4 different functions you have to evaluate. The homework assignment does not look particularly terrible. Like there's a few, like some of the graph stuff, which we'll talk about a little bit later, is a little challenging because it's new to you probably, but most of it is moderately straightforward, I would say. I am a fan of printing out the homework assignments. It makes it like just right. You can take it with you. You can look at it. You can write on it and then submit it later. So I encourage you to do so if you like to do that. And there is a question. I think it's the very last. I know we're kind of starting at the end. Interesting. finding the eigenvalues of a 2 by 2 matrix. So let's start with this 2 by 2 matrix. So how do we find the eigenvalues of a 2 by 2 matrix? Well, of any matrix really, but specifically 2 by 2, we take the determinant of A minus lambda times the identity matrix and set it equal to 0. So as a reminder, the identity matrix is the matrix that has 1s on the diagonal and 0s everywhere else. And it can be any size. So the 2 by 2 identity matrix is 1, 0, 0, 1. And just for reference, the 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. 1's on the diagonal, 0's everywhere else. So if we're doing determinant of A minus lambda times this, lambda times the identity matrix is just having lambdas on the diagonal. And then we're going to find the determinant of, now I'm kind of showing maybe more work than I need to. What we typically just do is you subtract lambda from each diagonal element. So I'm going to have 2 minus lambda, 1, 4, 5 minus lambda. This is your A minus lambda times the identity matrix. It's nice. And then the determinant of any matrix, well, back that up. The determinant of a 2 by 2 matrix, if I want to find the determinant of a general 2 by 2 matrix, I always like to say it's the product of the diagonal elements minus the product of the off-diagonal elements. It is a more challenging computation for larger square matrices. Luckily, we don't have to deal with that. We are only, or should only ever be asked to find eigenvalues of 2 by 2 matrices in this class. If 3 by 3 comes up, let me know.
I think maybe we had to find determinants of the 3 by 3, but we didn't have to do the eigenvalues.
Right, yeah. But I don't think you should have to find determinants of 3 by 3 in this class. You probably had to in 17B because they want to be like kind of more generally linear algebra focused. But really the point of this is to be able to do it for 2 by 2s, because that's what's going to allow us to eventually classify what kind of linear system of differential equations we have. Whether we have a spiral, whether it's a stable or an unstable equilibrium. So those are the things we're going to be using this for at some point. So let's see. If I take the product of the diagonal elements, that's going to be 2 minus lambda times 5 minus lambda, minus the product of the off diagonals, which is 4 times 1, and set that equal to 0. The nice thing about 2 by 2s is you're always going to get essentially what's going to be a quadratic equation. So I'm going to multiply this out. Negative lambda times negative lambda is lambda squared. 2 times negative lambda and 5 times negative lambda is minus 5 minus 2 is minus 7 lambda. And then 2 times 5 is 10, and 10 minus 4 is 6. Now, fair word of warning here. Sometimes these are going to work out great. Sometimes these are going to work out terribly. You're going to get nasty, irrational solutions, meaning you're going to have to actually use the quadratic formula. And you're also going to get imaginary answers. Sometimes you are going to get square roots of negatives because those are going to correspond to your spirals. So just be aware, these are not always going to work out nicely. You are going to get not pretty imaginary solutions to this, or complex if you want to use that. This one works out nice, right? This one factors as lambda minus 6 times lambda minus 1 equal to 0. So our eigenvalues are lambda equal to 6 and lambda equal to 1, which is great. Done. We're not going to get into finding the eigenvectors right now, although that is something you should have seen last quarter. That we'll revisit that once we get back to this part in class. Let's do a couple more examples. So let me ask you all to find the eigenvalues for this matrix. So find the eigenvalues for B equal to 7, -9, 0, 8. Go ahead and find the eigenvalues for that. You all at home or wherever you are on Zoom, you should also find the eigenvalues for that. So I will mention, you don't actually have to multiply this one out, because it's already kind of factored. Let's take a look. So if I do the determinant of what is it, lambda I minus b, or sorry, I got that back. But so I did write it. Technically, you can do it either way, lambda I minus b or b minus lambda I. But I should do it the way that we almost always do it in this class is b minus lambda I. So that's going to be the determinant of, let's see, b, so 7 minus lambda, -9, 0, b minus lambda. And if I multiply that out, it's going to be 7 minus lambda times 8 minus lambda minus -9 times 0 equal to 0. Okay, check this out. That's 0. And so look what you're left with. You have 7 minus lambda times 8 minus lambda equals 0. You could totally multiply that out and then refactor it. And you could do that and you multiply it out, factor it back. And I guess if you factor it back, you probably get lambda minus 7 times lambda minus 8 because of the way we usually factor things. But it's already factored for you. So the thing is, when this part's 0, it's super duper easy. We're going to get lambda equal to 7 and lambda equal to 8, which not coincidentally are those numbers right there. It is not a coincidence. That is a thing that happens all the time. So I want to point out, let's go back a second. It didn't happen here, right? Our eigenvalues were 1 and 6, and 1 and 6 are not, well, I guess 1 is technically right there, but 6 is not in the matrix, right? So what's different from this matrix and this matrix? What's the kind of important thing that's different? Yeah, bro.
The 0.
The 0. When you have a 0, either in that corner or in that corner, so 0 in either spot means your eigenvalues end up being whatever's on the diagonal, which makes life super duper easy. So a lot of times you will see examples on exams or some homework assignments where you end up having a 0 in the lower left corner or the upper right corner. And that means you don't have to do any work to find the eigenvalues. They are just whatever is on the diagonal, which is great. So one more quick example. If my matrix C is, I don't know, 6, 0, -92, and +13, I don't have to do any stupid work. I know that my eigenvalues are 6 and 13. Done. Which is great. So definitely take that, right? Like take that to heart. It'll definitely show up later on. Yeah, it's kind of cool. Let's do a few more matrix things just because we're already in the realm of matrices, and then we will talk about the 3D graphing stuff, all that stuff. Yeah. So 2 more things. There are 2 more questions on your homework about matrices that I feel like we can address. Let's do one matrix multiplication. It's going to be kind of terrible. So let's say we have, I don't know, I'm just going to make things up. 6, 2, 1, 0, 3, -4, 5, 2, -1. Times, let's not make it too awful, James. 1, 3, -2. So just as a reminder of how matrix multiplication works, when you're going left to right, you're always doing rows of your left matrix dotted with columns of your right matrix. So people say we're multiplying the row by the column. So I'm going to multiply this row by this column. But what I really mean when I multiply them is I'm multiplying 6 times 1 plus 2 times 3 plus 1 times -2, which is the dot product of those 2 vectors, for lack of a better word. Right? I think you probably talked about dot product in 17b. When you take the dot product of 2 vectors, it's just each component multiplied together, and then you add up the results. The only requirement to use a dot product is your vectors have to be the same size. So that's why, just for example, this doesn't work. This next example. You can't multiply, say, a matrix that's 2 by 3 by a matrix that is, I don't know, 2 by 2. because the length of the row here has 3 entries, and the length of the column here has 2 entries. And you can't do the dot product of that row with that column. So the inner dimensions of matrices have to match up to be able to multiply. Again, I don't think that's going to come up too much in this class, but there is an example on your homework of multiplying matrices, so I thought we should talk about it just a second. So if I multiply this row by this column, I end up getting 6 times 1 plus 2 times 3 plus 1 times -2. And then this row by the second column is going to give me, or just the second row by the column is going to give me 0 times 1 plus 3 times 3 plus -4 times -2. And then finally, the last one is going to give me 5 times 1 plus 2 times 3 plus -1 times -2. So that's going to give me the 3 by 1 matrix, 10, 17. And then probably actually of the 4 of these matrix questions, maybe the most important one, you could argue it's the last one, but I would maybe argue it's question number 13. No, sorry, question 14 is actually right. Here's a system of equations. I'll make it simple. 2x plus 5y equal to 19 and 3x minus 4y equal to 7. I want to write this system as a matrix equation. And actually, I will say, when we get to the stuff where we're dealing with linear systems of differential equations, this is an important thing to be able to go back and forth between. So it's not the only way we think of matrices, but one way to think of what a matrix is representative of a linear system of equations in so many variables. So here's how I'm going to write this as a matrix equation. So here's my coefficient matrix. So titled because it's literally just the coefficients of x and y. So coefficients of x go in the first column, coefficients of y go in the second column. Here's my variable matrix, x, y, and here's what it's equal to. That matrix equation literally says the same thing as this system of equations. Because if you read the first row times the first column, it says 2 times x plus 5 times y equals 19. And if you read the second row times the first column, it's 3 times x plus -4 times y equals 7. It's exactly the same as that. So being comfortable with going back and forth, maybe not so back and forth, but at least in one direction, getting from a system of equations to the matrix equivalent is a good skill to have because it will come up often. Because what we're going to have is systems of differential equations where you have like the derivative of x is equal to 5x plus 2y, and the derivative of y is equal to 3x minus 7y, and then you're going to want to change that into a matrix equation. So then we can look at the eigenvalues of the matrix to see what kind of solutions we have. That's where I've said it like 3 times already. That's where we're going with all this, is eventually want to look at systems of linear differential equations, maybe some nonlinear ones too, and see what kind of solutions we have, whether they're stable or unstable. All right, enough remembering of matrices for now. Let's get to what's going to be coming up in your more immediate future, which is some 3D graphing analysis kind of stuff, for lack of better phrasing. So I can't remember. 17B, did we do any kind of 3D graphing? A little? Okay, good. Talk about level curves at all? It's okay if that doesn't make any sense, that's totally fine. It might not be. I don't remember the material from 17B particularly well. So let me grab my notes here. Here. There you are. Cool. So when you're graphing in 3 dimensions, there's a lot of analogies, or it's very analogous. It can be analogous to graphing in 2 dimensions, meaning a lot of the same kind of things happen. So let's graph, for example, the equation 3x plus y plus 2z equal to 6. So here's what I would observe about this before we even start going. all of these variables are raised to the first power. In 2 dimensions, that means we would get what, like if you had an equation with just x and y to the first power, what kind of graph would you have? A line, right? It's a very linear. The same kind of thing is true here, except instead of being a line, we kind of have an extra dimension to play with. We have now a plane. So when everything is raised to the first power, or you don't see a variable, usually means you have a plane. It always means you have a plane. So here, just like if I was graphing a line, I would find the x and y intercepts. I'm going to graph a plane. I'm going to find the x, y, and z intercepts. So to find the x-intercept, we're going to set y and z equal to 0. And we're going to get 3x equal to 6, which is going to give us x equal to 2. To find the y-intercept, everything else is 0. We're going to get y equal to 6. To find the z-intercept, everything else is 0. So we're going to get 2z equal to 6. So z is equal to 3. So those are our intercepts. Most people, when graphing in 3 dimensions, set up their coordinate system this way, where z is going straight up, y is going to the right, and x is coming out towards you. That is how most people in math draw their coordinate systems. In physics, it can be different. I usually like to think of it as like, that corner of the room. So if you look at that corner of the room, that edge is the z-axis, that edge along the wall is the y-axis, and that edge coming out towards us is the x-axis. That is how I typically like to think of it. Whatever the case, it is important, like some people draw this differently. Some people do it like this, which is kind of weird to me. They do x to the right, z going up, and y going back away from us. I don't love that personally. It always weirds me out. I should say positive y, right? These are all the positive directions. So back this way would be negative x, negative y, negative z. Whatever way you orient things, there's one rule that you have to obey, and that is the right hand rule. Don't use your left hand, use your right hand. Meaning, so what do we mean when we say the right hand rule? It means if you stick your fingers along the x-axis, and right hand rule, nope, I just touched the thing. Sorry. So do you use your right hand when we talk about the right hand rule? Sorry, now it's broken forever. I've done it. It's not really broken forever, but let's try it. Unplugging and plugging back in. Because they're very finicky over here. Sorry. Yes. Okay, let me come back, please. No. There we go. Okay, but now we need the. Okay, fine. Sorry, 1 second, please, while I deal with these technical difficulties that were caused by me stepping too closely to things. Okay, great. Oh, I need to show that to young people. Okay, so finally, as I was saying, the right hand rule, take your right hand, put it in the direction of x, curl your fingers towards the y-axis. So right, it's kind of weird, like you're basically like this way, okay, like so that way, curl towards y, and then your thumb should point in the direction of the z-axis. So that's why we don't like to do it like, it would be really not great if we did it like this. This doesn't work. If I did it like that, if I put my fingers in the x direction now and curl them towards the y direction, my thumb is not pointing in the z direction, it's pointing away from the positive z direction. So right hand rule is usually how we graph things in math. Sometimes people do different things in physics. I'm not a physics person, so whatever. Anyway, so graphing this, I'm going to plot my points. I've got x equal to 2, y equal to 6, and z equal to 3. And then here is the plane. or at least part of the plane. Just like in 2 dimensions, we never draw the whole line, we draw part of the line. But there's the part of the plane that's in the first quadrant, the first octant, I should say. And the origin's kind of behind it. What else to say about this before we get going here? Yeah, let me look at, sorry, so many papers. Let's see, what kind of questions are you guys being asked? Okay, all kinds of. All right, let's get to that because that's what's the hardest stuff, sure. So let's look at a couple more examples. Let's say that we want to graph something like f of xy equal to 9 minus x squared minus y squared. Or if you prefer, so just like we do y equals f of x in 2 dimensions, we have z equal to f of xy in 3 dimensions. So we were typically thinking of the height, the z thing, as a function of x and y. It's not always the case, but it's often the case. So if I was going to graph this, well, often when we graph things in 3 dimensions, there's a couple techniques to use. One is to find what are called the traces. The traces are what we have in each of the 3 coordinate planes. So in the, and again, sorry, so for those of you on Zoom, I know it's a little hard for you to see this because I'm kind of pointing to corners and walls. But if you look at kind of a corner in your room, right? If you imagine that corner to be the origin, then I'm thinking of, right? If I'm sorry, I know I'm off screen here, right? I'm thinking of the corner away from me as the origin. This left wall is the XZ plane. That wall there is the YZ plane, and the floor is the XY plane. So, in fact, before we let's give ourselves time to talk about that before we get to graphing this papers. So, when we're looking at the XYZ coordinate system, the floor is lava. You guys seen that show? Floor is lava. I mean, it's ridiculous, but so that there's your XY plane. And then back here is your YZ plane. And then over here, which is always kind of the funky one, is your XZ plane. And the idea is to kind of help us see what a graph of a 3-dimensional surface might look like. We look at what the graph looks like in each of those 3 planes. And now, let me ask you all, if we're in the XY plane, we know something. We know that one of the coordinates always has a value of 0. Which one? If I'm down here on the floor, I haven't gone up, I haven't gone down, that must mean that z equals 0. And over here on the wall I'm facing, I haven't gone forwards or backwards, I must have the x equals 0. And over here on the left wall, I must have the y equals 0. So that's how we see what's happening in each of the 3 planes, is we find the traces by setting one of the variables equal to 0. And whichever variable is equal to 0, you're in the plane of the other 2 variables. So to see what this looks like, I'm going to look at all the traces. So the trace in the XY plane. So if I set z equal to 0, I'm going to get 0 equal to 9 minus x squared minus y squared, which becomes x squared plus y squared equals 9. And that's a circle. There's a lot of circles when you graph stuff, I will point. Like it's kind of a feature of graphing things in 3 dimensions is often you get things that are circles coming up in one of your planes. in the YZ plane, so that's setting x equal to 0, I'm left with, let's see, z equal to 9 minus y squared. I suppose I should graph them, right? I was actually like, so in the XZ plane, so XY plane, I have a circle of radius 3. In the YZ plane, I have a parabola. 9 minus y squared, a parabola that opens downwards like this. And in the, what am I left with? The XZ plane, setting y equal to 0, I'm left with z equal to 9 minus x squared. Also the same parabola essentially, except on the x-axis and the z-axis. Those parabolas are the same. So what I'm going to try and do is imagine, okay, sorry, I keep walking away. Imagine this in the wall I'm facing, this turned perpendicularly, cutting out, so I've got like these two things on top of each other, and then below a circle. So check it out. So here's kind of the terrible way of doing it. So I've got my parabola going down that way in my YZ plane. It's hitting the point right there, right there. And I've got my parabola going down this way in the XZ plane. And then I've got my circle on the bottom in the XY plane. There's my downward opening parabola. What to say about that? It doesn't stop there, right? It does continue downwards, but right, just like with almost any graph, and it does continue getting larger downwards, right? You have to stop somewhere, right? You can't graph the entire thing because it goes on forever. So that is often a way that people make some sense of graphing in 3 dimensions, is by trying to see what the traces look like and then combine that into one 3-dimensional picture. The other thing I should mention about this, and this is actually probably of this whole thing, this is probably the part that's going to carry forward mostly in the future, is what are called the level curves. And if I have enough room here, I don't really. So the level curves, I would say, are easiest to imagine if you've ever looked at a topographical map. So like, you know, like the maps that have like the lines on them that show you the elevation of things. Those are level curves. A level curve is just a curve, and it doesn't have to be like a function, right? It could be a curve on a map that shows everything at the same level. Right, on one of those curves, I'm sure there's a picture of this. On a level curve, all of the things at that quote unquote level are at the same elevation. So here's some pictures from your book. Now this one, that's not my favorite picture. Here's a picture from the book. So it's kind of not the best, but whatever. So here you can see on this map, like right here, this curve here that I'm tracing with my pen on my book, feels a little terrible. That's all the height of 2,000 meters. So what I'm thinking is I'm taking my mountainous range here, I'm taking a plane that is 2,000 meters high, and I'm slicing the range with that plane, and I'm left with that curve. That all happens to be exactly at that height. That is what a level curve is. I'm going to say it one more time to say it again. Level curves is just whatever you're left with when you look at all the things that are at that height and only that height. So in the context of this example, I could say, well, I'm going to pick a height. And when I say height, I really mean the z variable. I'm going to pick a value for z. So we're going to set, hopefully I'm not going to run out of here. Let's say we're going to set, well, we already did one. One of our level curves was z equal to 0. And it left us with the curve x squared plus y squared equal to 9. A little zoomed in there. That's a circle of radius 3. We could go higher though. Let's go a little bit higher. Let's say I want to pick z equal to 1. That's going to give me, so I should point out, I don't want to do really a lot more work than I have to do. Not because, well, I mean, I am lazy, but not because I'm lazy, because I want to be efficient with my time. I don't want to, every time I'm doing this, set z equal to 1 and then solve the equation. I'm like, okay, z equals 1, so I've got 1 equal to 9 minus x squared minus y squared, and then rearrange that to get x squared plus y squared equal to 8. What I really want to do, yeah, I'm gonna have to go to the next paper here. What I really want to do for my level curves is say, let's be smart about this. I'm going to take my equation, z equal to 9 minus x squared minus y squared. And for some reason that I couldn't really say, but I guess makes sense. We usually like to say, we're going to pick level curves at height C. So for some reason, we like to replace Z with C and then work from there. It doesn't really make a lot of sense to me. We don't really, it seems like an extra superfluous step here, but whatever, it's what we do. C is supposed to represent like, it could be any different number, whereas Z is like a variable. So I guess that's why we're doing it that way, but it seems a little extra to me. So we're going to replace Z with C because that's the way people do it. And then we're going to write this in a way that looks nice to us. And I will say there are typically two different things that are going to happen. Thing one, which is going to happen here, is you have an x squared plus y squared, and you want to get essentially x squared plus y squared equal to some stuff. The other thing that's going to happen is you're going to have something that is solvable for y, and you're going to want to isolate y. Because we know how to graph y as a function of x typically. So those are the two things that can happen. You're either going to get an x squared plus y squared, maybe you're going to get an x squared minus y squared, which is not the same as a circle, unfortunately. But here, what we're going to do is we say, oh, I'm going to add these over here. And I'm going to subtract that over there. And that's going to give me a circle. So this is a circle. The center is the origin. And the radius is, well, it depends on what C is. If C is 0, the radius is 3. If C is 1, the radius is the square root of 8. Generally, the radius is the square root of that number over there. Okay. So then, I can use my cup. Oh, I've got, yes, it's time to use the coloring pen. So, maybe, okay. So for, I'm really thrilled about this. So for C equal to 1, I forgot to see, we have a radius of the square root of 8. And yeah, for C equals 0, we have a radius of 3. And for, C equals 2, we have a radius of square root of 7. And so on, right? I mean, we can keep going. There is a point to this. For C equals 3, the radius is the square root of 6. For C equals 4, the radius is the square root of 5. Finally, a nice one. For C equals 5, the radius is the square root of 4, which is 2. And we keep going. For C equals 6, the radius is the square root of 3. For C equals 7, the radius is the square root of 2. And finally, for C equals 8, the radius is the square root of 1. Kind of hard to see. What people do with this is they make a level curve graph, or for lack of a better term, a topographical map of your curve. So I'm going to try and draw this so it's not too terrible. I might not graph all of those because it's too many to graph. So let's see. So let's do this too. So 1, 2, 3. So when C is equal to 8, I get a circle of radius 1. Oh, yes, of course, anytime. And then when C, so I'm going to pick the low-hanging fruit first. When C is equal to 5, I get a circle of radius 2. And when c is equal to 0, I get a circle of radius 3. So these circles are at a height of 0 and 5 and 8. Which makes sense because as you go, right, higher on the curve, I can't see it all, sorry. Hold it, fine. As we go higher, right, here at the bottom, you have a circle of radius 3. And then as you go up, you're going to get this way. So as I go up to 5, right, here's my circle of radius 2. As I go up to 8, here's my circle of radius 1. So that's the idea, is that these level curves here are corresponding to those level curves there. Okay, so here's the question that you'll need to be able to answer to do some of these homework problems. Are these level curves, in fact, let me read the possible answer here. So if I was asking this question on your homework, I would say on a piece of paper, sketch a set of level curves, f of xy equal to c, with equidistant values of c, which I did not do here, right? These are not equidistant values of c. I could have graphed all of them. I didn't want to graph all of them. We got time. We could have graphed all of them. So also, right, you don't have to graph all these things by hand. Remember Desmos, right? So, so if we graph all these circles, so, okay, fine. I know we can graph, I know we know how to graph circles. Let's actually delete that for a second. I want to copy that. Sure. Let's see if we make this quick. Oh, no, not that. That wasn't quick. Oops, that's okay, fine. Okay, that seems like enough, I think. So let me ask you, for these equally spaced values of C, am I getting a collection of equally spaced concentric circles or a collection of unequally spaced concentric circles? Those are unequally spaced, right? The radii are not the same distance from each other each time. So that's something I just want to point out, is that depending on what's happening with your different values of C, you might have equally spaced things or unequally spaced things. And it kind of takes a little bit of analysis here. 1 second. I promise you. So looking at what I drew instead, like if you weren't using Desmos, I can see that, look, these are equally spaced apart, but for unequally spaced values of C, right? From here to here, C, it went up by 5. So I increased 5 and my radius got 1 smaller. And from here to here, I went up by 3. I increased 3 and my radius got 1 smaller. Those are also not equally spaced out because I'm not going as much in as I am going up. Yeah. Like, I guess you mean like that they're getting closer and closer to each other. Yes, in that it means that our curve, right, is doing this kind of thing at the top, right? So each time we move, right, if we move, or actually it's going down, sorry. Brain. Oh, really? There we go. So, right, as we go further out, they're getting, so I should say, as we're going lower, right, because these are lower values of C, right? When C was 8, we had a circle of radius 1. So as we go down, right, our radii are getting bigger. But every time we increase this number by 1, the radius is increasing by the square to the square root of that. So from 1 to the square root of 2, the distance is about 0.41. From the square root of 2 to the square root of 3, square root of 2 is about 1.41, square root of 3 is about 1.73. The difference is less. So the thing is, basically, we're looking at the square root function, and as you go along the square root function, you increase by less and less each time you move 1 over. So that's what's happening. On the other hand, So again, let me reiterate, the kind of bigger takeaway from this particular problem is to get an idea of what's going on with these level curves. The level curves are kind of all the things that are happening with this 3D graphing, the level curves are kind of the more important piece. To be able to be like, oh, I can look at this map of this function or this actual literal map of the world and have an idea of what the topography looks like based on the level curves that are on that map, right? If I said, I'm just gonna make something up that's not, I'm not the best drawer, so I'll do my best here, but like if I said I had this kind of, this is gonna be not low. So like this is a height of 100 feet. This is a height of 300 feet, 500 feet, 700 feet, 900 feet. Wow, my writing. Like the idea is I can look at that and imagine this down at the base. And then as they go up, I'm in, up, right? I mean, obviously like a lot of, right? You don't really go up and out like that usually, unless you're in like Arizona with the cool kind of rocks. But right, the idea is that I can take this and be like, okay, well, I have an idea. This kind of would look like, and see, and again, I apologize. The drawing skills, not the best, but right, like the idea is we would kind of see these level curves on this actual surface in 3 dimensions. Again, it could be better. I'm not gonna, that's not gonna get scanned and uploaded because it's ugly. But you can take, in fact, and so that's those are some of the questions like on your homework. There's one question. This does not do well with the printing out, where they give you these 3-dimensional surfaces and they ask you to identify the level curves that go along with that. So you're kind of be like, okay, well, and that's where you have to really, again, you can't really see it very well in here. Like I can barely make out the numbers on here, but you have to pay attention to if things are positive or negative. If the level curve values are getting bigger or smaller. Like for this one, yeah, for this one here, it kind of looks like an upward opening parabola. So I would imagine at the lowest level, I have like a point, and as I go up, I'm going to get bigger and bigger circles. So the higher level curve values, excuse me, should have larger and larger and larger and larger circles, which is probably going to be either this answer or this answer. Probably not either of those because they're not centered on the axis, but it could be one of those. Kind of a process of elimination thing. Let's look at least 1 or 2 more examples because yeah, we got 10 minutes. Oh, let's do that. Let's do one of those. So, sure. I want to pick something that's not too terrible. I don't want that. Oh yeah. Sorry, I'm trying to like think of something that's not terrible. Let's say our function was square root of 9 minus xy. Oops. So unlike the previous example, this function also has a domain restriction. So here, there are some values of x and y that are just not going to work. For example, x equal to 2 and y equal to 5. That's not in the domain, because if you do that, you're going to get square root of negative. So here, before we do anything else, we should talk about the domain. Here, our domain is that 9 minus xy had better be greater than or equal to 0. Now, to me, that's kind of weird, right? Like, I don't actually really know what that looks like. So what I would probably do is try to solve this for y. So I'm going to do 9 bigger than or equal to xy. Dividing by x is kind of dicey, though. So here's what we're going to get. I'm going to rewrite it as xy less than or equal to 9. And then we have to kind of break it up. If x is positive, then I just divide by x. And I get y is less than or equal to 9 over x. That's weird. I don't really mean it. Go away. fine, don't go away, be there. Okay. 9 over x. So here's what I'm thinking. Here's what 9 over x looks like. It's definitely got the point 3, comma 3. It's definitely like that hyperbola shape where as x is close to 0, you got a vertical asymptote. As x is really, really big, you got a horizontal asymptote. What does it mean that y is less than or equal to 9 over x? Am I on this side or this side? Well, here's an easy way to tell. And this is actually true for most. This is kind of a more complicated domain question than a lot of domain questions. But the way to tell is to pick a point on either side. I pick the point 1, 1. If I plug in 1 for x and 1 for y, is this inequality true? Is 1 less than or equal to 9 divided by 1? Yes. So that means that the point 1, 1 is on the right side. It's on the side where we are, sorry, brain, where the side where this inequality is true, where x, y is less than or equal to 9. Now this one's a little extra complicated because we're having to restrict it here. So really what I'm saying is we want everything over here, but I'm staying on the side of x being positive. Now, if x is negative, something different is going to happen. Okay, so if x is negative, so I'm going to remind you, x is negative. I know I just said it twice, but I want to point out. So if I take this inequality and divide both sides by x, which is negative, what do I get? Why does it change directions? Because x is negative. That's why this one's a little extra tricky. I didn't actually mean to pick a tricky problem, but I just kind of made it up on the fly. And sometimes that happens. So over here, when x is negative, here's the other half of this graph. It has the point -3, -3. And I want y to be bigger than or equal to 9 over x. So I want, let's test a point like -1, -1. So if I plug in -1, -1, let's see, is -1 bigger than or equal to 9 over -1? It's a good question, is it? Is -1 bigger than or equal to -9? Yeah. So that's the side I want of this graph. So I want all of this as well. I'm really loving this new pen. Now, I should point out, I haven't addressed the x-axis yet. Is the x-axis included? Correct. So far, I picked x bigger than 0, which is everything on the right of the x-axis. I picked x less than 0, which is everything on the left. What about x equal to 0? Does that satisfy this inequality? For sure it does. Because if x is 0, 0 times y is for sure 0, which is less than 9. So we get that too. So this, I know my picture is devolved into horribleness here. All of this is your domain. Kind of weird. So typically, when you're talking about domains of functions of two variables, your domain is a region in the xy coordinate system. Yeah, I got that. That costs a little fast, by the way, just so you know. It's like 252 and 255. I'll do one more example with domain in a second. But I was going to say level curves. Oh, be quiet. I just think I talked to you. Okay, so the level curves of this. So this is where, again, you're going to say, well, set your thing equal to c. So set c equal to the square root of 9 minus xy. And since I don't see like an x squared plus y squared kind of deal, that's where I'm going to solve for y. So I'm going to square both sides, add xy to the left, subtract c squared to the right, and then divide both sides by x. No, that's fine. Yeah, it's not inequality. You don't have to worry about that. Provided x is not 0, right? Okay. So this is what my level curves look like. So for example, if, and here's where we can be, can C be negative? It depends on where you look. Here, it totally looks like it could be negative just fine. If you look up here, when you take a square root of something, what kind of numbers do you get out? Only positive, or 0, you get 0 too. So C actually can't be negative. So when you're thinking about the values of your level curves, you have to kind of be thoughtful about what is in the range of your function. So C has to be non-negative here. So let's start with C equal to 0. So C equals 0, y equals 9 over x. If C equals 1, y equals 8 over x. If C equals 2, y equals 5 over x. So graphically, here's what this looks like. Yeah, I should have used different colors, sorry. So we'll do C, so 9 over x. Always a challenge here. 1, 2, 3, 1, 2, 3. Okay, so I'll do y equals 9 over x in red. At this point here, this is going to look kind of wacky because I'm drawing it kind of big. It's the same thing over here. And then 8 over x is a little lower, right? 9 over x has the 0.33. 8 over x doesn't have the 0.33. If x is 3, y is a little bit less than 3, right? 8 over 3 is like 2 2/3. So I'm a little bit lower. All right, and this is where my drawing skills start to fail. And then, so, and we usually label this. So like this is C equals 0. This is C equals 1. This is C equals 2. So if we were trying to think about what this thing looks like three-dimensionally, it's not easy to do, right? You've kind of got these things on the sides, and as you go up, you're kind of moving inwards like these kind of walls. Now, the nice thing is, I'm very jealous of you for all this. You live in an age of more advanced technology than I did when I was taking this class, these types of classes with 3D graphing when I was a student. So if you do go to, where are you? Graph. This is definitely a link in Canvas. You can totally graph this. What was it? Z equal to the square root of 9 minus xy. Cool. Look at that. Now you can kind of totally see what I was talking about, I think, right? Like you can see, well, in fact, let's find some level curves. Oh, come on. Yeah, fine. Let's go higher. So if you look at this, right, there's the plane z equals 1. And if you look at where it's being cut, let's kill this other one here. Right, if you look at where the graph is cutting it, you can see kind of the hyperbola that I was graphing on. Right, there's your level curve, c equals 1. I think everything you can see it, right? Kind of. Maybe a little. It's maybe easier to see if you look there, right? Literally that part there and that part there. Or maybe there. You can kind of, right there it is right there. It's where they intersect. It's kind of neat. And you can go higher. And there's another level curve. Well, that one's an interesting choice. So that level curve, yeah, I should mention that one real quick. That level curve is actually the coordinate axis. So if we go back to our example real quick, I know it is 259, 258, so I will wrap it up here. But if you go back to the level curve, if you let c equal 3, you're left with y equal to 9 minus 9 over x, which is y equal to 0, which is the horizontal axis, but it's also, so the thing is, when you solve for y, sometimes you get a little bit dicey. If you go back to the actual original equation, you have x times y equal to 9 minus c squared. So you have x times y equal to 0. That actually leads to two lines. It leads to either x equal to 0, which is the vertical axis, or y equal to 0. So if you look back, right, so it's kind of weird to graph it, but this is the level curve when c equals 3. Kind of funky, but you can see it. It's there, right? Literally, this plane is intersecting that surface along the line, right? Along that line right there, and that line right there, which is exactly y equals 0 and x equals 0. It's kind of cool. So that's the idea of level curves. The level curves are the two-dimensional curves in a particular plane at a certain height that are where that plane intersects the surface that we're looking at. So it's all of the surface that happens to be at that particular height. Okay, it's just 3 o'clock. I should stop talking. I was going to give you another domain example, but we'll have to wait until Monday.